everyone. Today we are very glad to have Ming, who is from Monash University, he is a PhD candidate in computer science at Monash University, where he is currently being supervised by Prof. Shirui Pan and Prof. Yuanfang Li, and he is also a research staff at Meso Utotech and a research assistant at Monash University. Ming completed his bachelor's and master's degree at Hebei University of Technology and the University of Melbourne in 2017 and 2019, respectively. He has published over 10 top-ranked conference and journal papers and regularly served as a PC member and reviewer of major AI, ML, and data mining conferences and journals, including IJCAI, PAKDD, TNNLS, TKDE, and more. Ming's research interests mainly focus on graph neural networks and geometric deep learning, with a particular emphasis on temporal settings such as dynamic graph neural networks. He is particularly passionate about applying these techniques to tackle practical challenges such as time series forecasting, industrial process modeling, and anomaly detection. And today we will have him present neurotemporal walks, motif-aware representation learning on continuous time dynamic graph, which was a presentation at Europe's 2022.
Okay.
Yeah. And
okay, thank you,
yeah.
Eddie. So, yeah.
Yeah.
Shall we start
I think we can start.
Talk? Okay, yeah. So let me share the screen first. You guys can see my screen, right? All good. I should say good afternoon, everyone, and welcome to today's session about the sharing one of our papers that presented in the last NIPS conference in the last year. And the topic is the neurotemporal walks and motif-aware representation learning approaches on continuous time dynamic graphs. And in today's presentation, I'm going to talk about 5 parts. The first and second part is meaningful for someone new that's not familiar with the context of the dynamic graph learning. And on the third part, I will talk about our proposals in detail. And in the fourth part, I will discuss our main experimental results and followed by a summary section. Okay, let's start from some background information of the graph, dynamic graph.
Yeah. Sorry to interrupt. Just a quick question. Do you prefer us to leave questions to the end of the talk or during the talk?
Yes, please. Maybe end of the talk, I could adjust them more.
Okay, sounds good. Yeah. So let's have questions at the end of the talk.
Yeah, sure. Okay, so in this section, I will briefly talk about the concept of graph, dynamic graph, as well as the basic paradigm of the graph neural networks and the open questions that live on the dynamic graph learning. So firstly, we could say that many real-world scenarios, whatever the citation networks and molecular structure, as well as the traffic network topology, they were all kind of graph structured data in the real-world scenarios. And for the many real-world systems, they are actually dynamic. So in other words, the dynamic graph can abstract many real-world systems. For example, the social network that different users interact with others at different times. So this is a kind of social network evolving. And another example is the online shopping platform that's specific user purchase an item at a specific time. For example, on the Amazon and other kind of online shopping website, that kind of a dynamic graph that with the user item interactions. Okay, so regarding the taxonomies of the graphs that especially stand from the point of view of the dynamic graphs, there are 4 kinds of them. The first one is the static graphs. That means there are no temporal information involved at all. In that case, we have fixed graph structure and attribute information. And the kind of example is going to be the molecular structure. So given a kind of molecular, the structure is here. It looks like this. And one step further, we have the 8-widget graphs. So in this kind of graphs, the temporal information is involved on the attributive information. So for example, in this case, we have the dynamic nodal edge features, but we have fixed graph topology. And the real world example is gonna be the metro networks that with the fixed station topology. But we have the dynamic traffic volume at a different time in a day at each of the station. So you can see that many times, especially for the multivariate time series works, are built on this kind of abstraction, that they build the entire scenarios with the age-weighted graphs. And again, we step one step further, we see the discrete time dynamic graph. So for this kind of abstraction, it's a kind of specification of this generalization that calls the continuous time dynamic graphs. So in the discrete time formulation, we characterize the dynamic system with a sequence of regularly sampled static graph snapshots, as I demonstrated here, that is the G1, G2, and G3. The time interval between the G1, G2, as well as G2 and G3 are equal here. But the difference is that in each of the graph snapshots, we may have different structural as well as the attribute information involved, as you can see from this example. And considering the continuous time formulation I mentioned here, so in the continuous time dynamic graph, we formulate a dynamic system with a sequence of the temporal events that are irregularly sampled in the real world. So obviously, we can see that the continuous time formulation is a kind of generalization of the aforementioned 3 categories. So that's why, you know, in real world dynamic graph learning papers or with the works, there were more and more work that focus on directly learning on the continuous time dynamic graph, because this is the kind of, I would say it's one of the most generalized formulations to characterize the real world scenarios. Okay, another concept before we dive into the world of the dynamic graph learning, this is the message passing graph neural networks. So the MPGN for short is a kind of popular simplified paradigm in modeling the real world graph structured data. So I call it simplified because this paradigm is actually a low pass filter that aggregates the information from the neighbors. And to some extent, we can see this kind of paradigm as a specification of the spectral graph neural networks, but that's another story. So I will not talk too much details here. So in the message passing graph neural network, as I said, our end goal here is to aggregate the information from the multi-hop neighbors. For example, we can see that in this picture, in this example, the C, B, and E are the first order neighbors of the target node A, and F obviously it's the second hop neighbor that's from the with respect to this node, target node A. So in the computational, we see the aggregation flows. We can see that the BCE appears here in the first layer. So in this layer, we aggregate the information from the first neighbor, from the first order neighbors, that we aggregate the information from BCE. And of course, the F appears here as the second hop neighbors of the target node A in the second layer here. So in this computational flow, we see that this dashed arrow is represented the generated message, and the block here, the grid block here, is the aggregation function that aggregates the information from the neighbors, and then we use the aggregated information to update the representation of the source node. And here is the formal definition of the MPGN. So firstly, we initialize the node representation with the raw information, for example, with the node feature here, and then we update each node representations over the following paradigm. So firstly, given a source node V and one of its direct neighbor U, we calculate the message first. That is the dashed arrow in the previous slide example. Here with the message function, we use the node representations from the last layers of the source node and the direct neighbors to calculate the message. And then we use the, for each of the neighbors of the source nodes V, we aggregate the calculated message together with the aggregation function. And then we update the embedding of the source node V in the current layer with the by using the aggregated message and the information in the last layer. So this is the very straightforward idea of the message passing graph neural network. And on the top of this formulation of the GNNs, we have the problem of the graph representation learning. So the problem of the graph representation learning is one of the most fundamental research questions in the real world graph system that we aim to learn the low dimensional node or edge embedding vectors. So with this kind of low dimensional embedding vectors, it allows us to conduct certain downstream tasks, whatever the node level or the edge level classification, regression, and so on. And of course, in this paradigm, given the graph, we can map each of the nodes to the embedding vectors with the model G theta. And this kind of models, of course, it can be the anti-GNN as I mentioned. But given the examples on the static graphs, a common question, especially in our community, we're going to ask, like, how can conventional graph neural networks be extended, like, to model the continuous time dynamic graphs? So that's the question. It's trying to be answered in many recent advances in the dynamic graph learning. Okay, so then we pop down to the related works here. And here I'm going to introduce two mainstream methodologies that being used in many recent works. The one is the node-based approaches. That this kind of, or with this branch of method, they extend the concept of the conventional message passings to aggregate the temporal neighbors information. As you can see here, it's quite similar with the example I provided in my previous slide. And another branch of method is the subgraph-based method that's generalized the walk-based static network embedding method, like the deep walk and node-to-vect to model the dynamic graph. So so among this kind of method, the concept of the temporal random walks are widely used, right? So let's talk about the first category, the temporal message passing. So it's quite similar with the conventional message passing, but the difference here is we have the temporal information involved. So firstly, again, we initialize the time-aware. Here is the time-aware node representation instead of time representation. So we initialize the time-aware node representation with the raw attribute as well. So here we use the x-weighted that denotes the node with attribute information at the time t. And then with the initialization of the node representations, we update the node representation with respect to the temporal graph structure and the attribute information. And here I highlighted the difference part compared with the static message passing. So during the calculation of the message, we also have the time interval encodings, or for short time encodings calculated here to enforce this mechanism to preserve the very important temporal informations. And during the aggregation steps, we calculate, or we say we aggregate the information from the temporal neighbors instead of the conventional neighbors in the static graph, right? So that's why here we have we denote it as the NVT. The T means the temporal neighbors of nodes of source node U at the time t. Okay, and then by doing the updating, that's quite similar with the conventional version. we can update the time of wheel representations of the source node V at the layer, at the current layer L. And for the calculations of the time embedding V, so the goal here is to taking the important time gap information into the content dimension to preserve such information during the message passing. And here is one of the most popular implementation in many recent works like the TGAT and TGN. They use the random Fourier encodings to do this step. And as I said, both the TGAT and TGN, the two very popular works that build on this paradigm just with some modifications. Okay, another category is the temporal random walk. So firstly, we define the temporal walk as the sequence of the nodes, but with the h times that I denoted here in an ascending orders. So that means we have a kind of walks that's from the most stale temporal node to the most recent temporal node. Okay, so in this kind of method that's using the concept of temporal walk, a very popular formulation is to using the scapegraft model to optimize the entire network. So the first step here is to do the initialization that we firstly we sample an initial age E from a distribution Fs that's based on a kind of temporal biased sampling mechanism that we by given this kind of probability that we are more desired to sample the age that's close to the current time, right? So this is the kind of temporal biased probability, and then given the initial age, we can sample the nodes in a walk from another distribution, of course. Again, here we can use the temporal biased sampling strategy as well to emphasize more recent nodes because they are usually more informative. And finally, given a set of sampled walks, we can finally learn the mapping function F by using the scapegram objective that maximize the co-occurrence probabilities of the temporal nodes in the walk. So it's quite similar with the deep walk as well as Motif-Aware, right? And in the community of the dynamic graph learning, we have both the CDDNE and the COW, actually based on the concept of the temporal walks. And the CDDNE is exactly following this paradigm to learning on dynamic graph, but COW just used the concept of temporal walk, but with other kind of designs. And of course, I would say that, before I pop it up into our proposal, I would say that our method can be regarded as one of the extensions of this method, COW. So if the readers are very interested about the details, you can refer to these papers for detail and compare with our papers, of course. Okay, so let's start from the motivations of our proposal, or say the challenges. So the first challenge here is the intelligent spatial and temporal dependencies in the real-world continuous time dynamic graph. They usually require a specific paradigm to model, as I mentioned in the related work. There were two stream methodologies to do it, but I believe there were more opportunity, we say the diverse methodologies to do this as well. And so this kind of challenge prevents the direct use of the out-of-shift GNNs. But we can see that many existing works that simplify the CDDGs to its discrete version that consists of a series of static graph snapshots with the uniform time intervals. So this kind of characteristics that allow this kind of methodologies to use the out-of-shift GNN like GCN and GAT combined with the squints model like the transformer and the RNNs to learn on the DTDGs, but at the cost of the model effectiveness compared with the learning method that's directly based on the CDDGs. even though there were some works that proposed to directly learn on the CDDGs like JODI and the DYREP, but actually the inductiveness of the pattern capture cannot be guaranteed because the raw node identity that is directly using in the modeling process. So that's how that's violates the inductiveness design of the dynamic learning models. Okay, so although there were some recent advantages that attempt to alleviate the aforementioned issues, whatever the inductiveness as well as the simplified formulations, there were some recent advances, like I mentioned, the TJTs and CALs. They don't have the aforementioned two issues, but they have other problems. For example, they usually fail to explore the diverse and expressive patterns during the learning process because they only focus on the temporal biased characteristics when sampling the patterns from the dynamic graph. But actually, in the real world, there are other aspects to be considered to allow to extract diverse yet expressive patterns. And I will talk about this later in the presentation. Another challenge is the temporal events in the CDDGs are usually irregularly sampled. So this results in a significant challenge when we trying to use the squints models, or we see the message cluster mechanism. That's why we had the time encoding used in this method. So here is an example to illustrate the idea behind the irregularly sampled. So what is that? In this example, we can see that the nodes A and C have a common neighbors of B at different times, T1, T2. And then on the point of view of the current time, T3, we see that the interaction intervals, the time intervals of the interaction, I would say, the delta T1 and the delta T2 are not equal. And in the real world scenario, these two numbers are going to be very diverse. So for example, T2 going to be a very small number, for example, 1 or 2 seconds, but T1 going to be a very, very large number. So how to get this challenge is another motivation of the work. As I mentioned, the previous methodologies typically bypass this challenge with time encoding techniques, but using the time encoding, so firstly, it's feasible, but using this kind of technique that makes the time dependencies being modeled implicitly, because the time encoding has been treated as a kind of attributing information. So if we model the temporal dependencies in such a way, we empirically find that it's gonna hurt the model performance. So in this paper, we have a more advanced implementations to model whatever the time as well as the structural dependencies, or we say the spatial dependencies in the dynamic graph. Okay, so here are some basic concepts used in our work. The first one is the dynamic graph motifs. So the dynamic graph motifs can be regarded as a kind of patterns that widely appeared in the continuous time, whatever the continuous and the discrete time dynamic graphs. For example, the pattern A, B, C, this kind of temporal walk, or we say the CBA, a kind of time reversed temporal walk, are such a kind of these patterns. But this kind of patterns has not been, obviously, the inductiveness of this pattern, if we directly use it in the modeling process, cannot be guaranteed because the node identity is directly used in here, right? So one of the most important steps is how to transform this kind of walks to the dynamic graph motifs. So I will talk about this in the next slide. But in this slide, so given such a patterns like CBA or ABC, we can see the dynamic laws behind that two nodes interact with the common neighbors that tend to interact in the future. So it's quite common in the social platform that if we have a common friend in the past, so after his or her introductions, we are going to meet each other in the future. And in this case, we see that the spade, star, and the club within a certain time range. In this case, it's 0, is between 0 and T3. It's gonna be dynamic graph motifs after the anonymization that we change for each of the nodes to a ship. So in this case, this is the kind of dynamic graph that describes the law I mentioned. So here in this work, we're mainly focused to answer two sub-research questions. The first one is how to extract diverse and expressive motifs, and the second, how we encode these motifs effectively to learn the time-aware node representations in the dynamic graph. So firstly, in this paper, we see in this work, we define the continuous time dynamic graph that's similar as in the previous work that at the stream of the temporal interactions here. Okay, and for simplicity, we assume that these kind of interactions are without node and edge attribute information in the following slide. But I would like to mention that, also emphasize that our methods can be easily extended to learn on the attributive CDDJs. We have demonstrated the details in the papers, like how we can simply to aid some terms in the methodology to do this. Okay, and here's some preliminaries. So the first, firstly, the definition of the dynamic graph motifs. So given a continuous time dynamic graph, we define the motif as a set of anonymized temporal nodes with the corresponding interactions within a certain time range, as I mentioned in the aforementioned example here. So this is the anonymized temporal node, and here is the interactions. But we need to assure that these two interactions in this example is within this kind of age. Is within this kind of range. So this is the definition of the dynamic graph. And by using the concept of the dynamic graph, the learning question turns to be how we can characterize a temporal node with its surrounding motifs. And if that's possible, the short answer is yes, we can characterize that temporal node with the surrounding motif, or we say the surrounding dynamic laws. That is what we did in this work. And here is the definition of the temporal work. It's quite similar with the temporal work that I mentioned in the previous slide in the related work, but the definition we use here is the time reversed version. That means the time here, the age time here is in the descending order instead of the ascending order. And as I said, after the anonymization, we can effectively transform the temporal works to the dynamic graph motifs. So that's why here we have this example to elaborate the idea behind. So here you can see that we have two different temporal works sampled from the system. That is the UBCU and the VEDV. But note that if we anonymize the node identities with the color or with a kind of shape, so we anonymize the identity of U with this kind of shape. So this node and this node gonna be the same one, and B is the red and C is the green. We can see that these two different works turns to the same patterns within this time range. So in this case, they were represented the same meanings in the same dynamic network. So that's why we have the first remark. So a dynamic graph motif here, it can has one or more instantiations, like these two works, right? So which are temporal works. And of course, we have the second remark that a valid temporal work can of course be generalized to a specific dynamic graph motif after the anonymization. So here is the very naive implementation of the work anonymization. So how we do that? Here's the formal definition, but I'd like to talk about it in this example. So how we do that? We use the smallest index of the node in a work as its position encoding. So in this case, we see that U appeared in the index 0 and index 3. But here we use the index 0 because we use the smallest index, right? So here the node U tends to be 0, and B tends to be 1, and C tends to be 2, and this is 0. So that's why it's represented this shape 0, 1, 2, 0. And similar here, we're gonna be 0, right? So 1, 2, 0. So same shape. And here is the naive implementation of the work anonymization, but we cannot use that directly in the methodologies because there were certain problems. I will talk about it later in the related discussion of the anonymization used in our method. Okay, so here is the our methodology. So firstly, we need to do the work sampling to extract the motive from the network. So we consider not only the temporal and the spatial constraints when we're doing this. So firstly, of course, we can consider the a kind of temporal biased sampling strategies that's quite similar with the one that I demonstrated in the related work. So in this case, we are more desired to sample the node that's more close to the current time. For example, if the current time is t equals to 8, we are more likely to sample this node f, because f has because there is an interaction appearing in the time 7. So f is more desired. And following these temporal biased sampling strategies, we have UFVD, right? And on the other hand, but merely considering the temporal biased information is not informative enough. For example, we can also consider the neighbors with higher connectivity because they usually allow us to explore more diverse but potentially exploitive patterns. For example, the B here has a larger degree compared with node F and node C. So I'm also like I would also like to sample this node, for example, that allow us to not only explore the node A as well as the C. So this is the spatial biased sampling strategies. So in that case, we have the UBVU, right? And in these two equations here, the alpha and the beta are used here. Is actually the sampling and biased intensity to control how should we emphasize such biased sampling strategies during the work sampling. But merely considering the aforementioned spatial temporal biased strategy information, is not enough because the spatial temporal sampling is actually emphasize the it actually can be considered to kind of depth first search strategies in the network. So that means given a specific sampling budget, we may likely to sample UFVD several times or UBCU, these two works many times, but leave this UCBA, to leave these patterns never being explored before. But these patterns may also be informative during the modeling process. So how can we balance the depth first search and the wide first search is the question. So here we design the a kind of the exploitation and exploration trade-off to balance the work sampling during the implementation. So here, if a temporal neighbors, obviously the temporal nodes have been sampled many times. For example, if I have sampled B or F many times, in the next sampling round, the sampling probability of these two nodes gonna decrease. Okay, so in that case, I'm more likely to sample the node C. So if I sample C, I can have this path UCBA. So that allow this path to be explored as well. And after the work sampling, we're doing the anonymization. So there are two objectives to do this part. So firstly, we inject the structure information with the positional encodings during the anonymization. And secondly, we maintaining the inductiveness of the proposed method by removing the raw node identity node identity that I mentioned. So there are actually two strategies we can use to implement the work anonymization. The first one is the unitary anonymization, and it's quite similar with the naive version of the work anonymization I mentioned before. So during the unitary anonymization, if for example, if I just sampled one temporal works by given the the target node U, if there were just one works, this kind of implementation turns out to be the naive implementation that I use the smallest index to be the positional index of the node identity, to be the node relative identity. So in this case, it's gonna be 0. Sorry, if I take the node F, for example, it's gonna the positioning encoding gonna be 0, 1, 0, 0, because the F appeared here, right? But if I have more than one works, for example, if I have another exactly the same works here, the positioning encoding of F gonna be 0, 2, 0, 0. So the unitary anonymization has a tight connection with the strategy that I mentioned before, right? And we can also consider in the binary anonymization that is built on the top of the unitary version. So during the binary anonymization, we establish the connection between two set of works, starting from the two target nodes U and V. So here we're unifying the namespace between two positional encodings. We bring them together by using the concatenation operators here. And this kind of positional encodings is conditional not only MU but also MV. So it's helpful it's helpful for some edge level tasks like the commonly used transductive or the inductive temporal link prediction. In this kind of tasks, this is gonna be helpful, as mentioned in call as well. Okay, so after the anonymization, we turn a temporal works to a dynamic graph motifs heads W, as mentioned here, and the anonymization operations are used here can either be unitary or the binary anonymization. That really depends on the downstream tasks. For example, if I prefer to conduct the node level task, I use the unitary version. Instead, I use the binary versions. Okay. And here is the another module that to encodes the motifs. So in the previous stage, we sample a set of dynamic graph motifs, or say the anonymize the temporal works. But how we can embed it is the question, because this kind of motifs are usually consist of irregularly sampled nodes. That's the time intervals between two temporal nodes are different in a work or within between the works or within a work. So in this case, we propose to explicitly integrate over multiple interaction time intervals to learn to drive the latent evolutions of the spatial temporal dynamics with the with those discrete observations, or we say condition on those discrete observations. So here is a demonstration that given an anonymized temporal work like this, we firstly map those discrete observations via the instantaneous activation process to the latent space. And then given the initial state, we solve in an ODE to drive the evolution of the latent spatial temporal dynamics to another point. And at this point, I activate the terminate state again with this discrete observation, and then treat it as a new start state to use in another ODE solving process. As I demonstrated here, the key is between lines 3 to 7. So in short, our methods interleaving two steps, the continuous evolution and the instantaneous activation processes to learn the latent spatial temporal dynamics. One of the things I need to emphasize why we have the spatial part here, because you cannot see the spatial here, right? But the spatial part, the spatial information involved during the anonymization stage, because we replace the node identity with the positional encoding, right? So that's another key point to combine those two stages together. All right, so during the continuous evolution step, that given us series of temporal nodes, for example, here, the notation denoted here, we first reverse that time reverse the temporal work. So it's quite intelligent, right? But firstly we need to assure that the anonymized temporal walk we have here is in the time intervals here is in the ascending order instead of the descending order to allow the ODE solving, right? So we're firstly ensuring that Ti minus 1 is less than Ti here, and then we solve the following ODEs to get the end state after one of the time intervals. So in this case, the ODE function f can be very diverse. So here we use an autoregressive GRU as the implementation, but you can also use other kind of networks to implement the ODE network. And for the instantaneous activation, it's quite the idea behind quite straightforward. That is trying to activate the end state of one of the ODE solvings with the discrete observations. So we treat the HI as the new start activations of another, or we say as the following ODE solving process. Okay, so the idea of this algorithm is quite similar with the one that we call the ODE RNN. So if you are interested, you can also give a more in-depth research on it. Okay, and finally, given the following model, we train the entire network with a harder contrastive pretext task instead of the BCD loss that's widely used in many works. So here, the key idea behind it, we are trying to maximize the mutual information between the interacting temporal nodes while we're pushing the irrelevant node pairs away. So those kind of irrelevant node pairs can be regarded as the negative samples, as demonstrated here, with a certain budget, of course. Like you cannot explore all of the nodes in the dynamic graph, right? Because it's too many node pairs to be explored. So we have the certain number of negatives to be set it at the implementation stage. And the function SIM here denoted the similarity function, and it can be any of the similarity function that you can use. For example, a very naive sigmoid activated linear mapping. Also, the non-linear mapping can also be used here. And here are some technical challenges before we can use the proposed method in the real-world scenarios. The first one is the batching, because imagine that we have a serial target node in a batch, for example, B. We have B target nodes in a batch, but for each of the target nodes, for example, if we have just one length while anonymize the temporal walk, we have to do big OB times ODE solving. Like we have to solve them one by one because we have different initial state, right? And we have different delta T. How we can do that like in the real world? For example, if I got many target nodes, we say the ODE solving in a batch. So the key idea here is to solve them, solve all of the ODEs at once. And here we employ substitute variable tricks to do this part, like to unify the integral time among all ODEs to be the same range. So in that case, we decrease the time complexity of the motive encodings from, in this example, of course, from the OB to the O1. Okay. But for the details, due to the time reason, I may not be able to elaborate too much technical details, but you can refer to the appendix B3 for more details. And another challenge is the time interval normalization. So there is the fact that in the real-world dynamic graphs, we see that the time interval distribution looks like this. So in this case, we can see the average time interval is gonna be the 23,000. It's a very big, large number. You cannot do the ODE solving within this kind of time intervals. It's not feasible. But how we can do that? We need to scale the time intervals down to a quite small range to enable the ODE solving. How we can do that? We can use a certain scaling, or we say the normalization strategies. For example, the constant scaling or the log scaling or the other kind of strategies. But we find that the key is to return the relative difference between the small and large time intervals, instead of to preserve the precise difference between them, because you preserving the precise difference can bring almost the same result here, but that's not necessary, and also infeasible with solving when learning on the real world scenario at the Fed, and the time interval is too large to be integral. Okay, so here's the experimental results of our method compared with the state-of-art method, for example, cow and the TGN Edward TGAT as well. So the last two lines are the results of our method on the task of the transductive and inductive link prediction. And in this example, this symbol denote our method with the binary anonymization, and this line denote our method with the unitary anonymization. So firstly, we can see that the two anonymization strategies can bring similar performance in some cases, but on some data sets like the MOOC as well as the Taobao, you can see that there is a certain performance gaps. Some cases the unitary anonymization help, and some cases the binary anonymization helps. So that's why we cannot say which one is better, but it's more related to the task as well as the data sets. And among all of the experimental full data set, we have a very strong performance even compared with the cow on the attributive here. This is the attributive data set, and the college message and error on non-attributive data sets. So you can see that the gap of both significant. And here is the result of the temporal node classification, that we also have the best or the upper performance compared with other methods like TGNs. We haven't included the result of cow because the cow is natively designed for the age level tasks. Okay. And here is the ablation result. So the green area, from the result on the green area that is related to the work sampling, we have this takeaway conclusion that the spatial temporal biased work sampling is highly preferred in most of the cases, but the traversal properties, considering such a kind of trade-off, may help on some cases, but in other kind of data sets, for example, college message, you can see the gap is not big. But on some data sets like Taobao, you can see this kind of exploitation and exploration trade-off can help. That their gap here is quite significant. And if you take a look of the variance 4, you can see that the proposed encoding strategy, especially for the evolution, continuous evolution process, is extremely helpful if we disable it, the performance drop drastically. And of course, the contrastive learning may help in some cases, but anyway, it's not our main argument in these papers. So it can bring general improvement, although the improvement are not very substantial. Okay, and here is another ablation study to focus on the modeling of the temporal dependencies. So compared with the standard RNNs, our method can bring significantly improvements because the standard RNN, as I mentioned here, this kind of approaches cannot consider the crucial temporal interval information, as I mentioned. This information is quite essential when formulating the dynamic graph motifs, or say the dynamic graph patterns. So we cannot neglect this information. And compared with other popular designs, whatever the exponential time decay as well as the time encoding, they cannot effectively model such temporal dependencies. And we can see that there remains a significant performance gap between our proposal and those methods that implicitly model the time information. And here's the parametric sensitivity study. And due to the time reason, I will not be able to dive into details, but if you are interested on some important parameters, whatever the sampling related one, as well as the number of natives, temporal walk length, as well as number of walks. You can see the details in the paper. But before we end, I would like to emphasize the obviously to discuss a little bit about the limitations of this work. So in this work, the first limitation is the calculation of the spatial bias. The probabilities can be computationally heavy, and this is one of the research direction in the future. That's how we implement the whatever the spatial biased sampling as well as the other components of the network if efficiently to make the whole things can be run in an online manner is going to be a question. And another one is the time interval normalization strategies can be more sophisticated. And as I said, that although we have a sample solution that's based on the log transformation, but in fact, in this paper, we haven't provided any theoretical guarantees of the stability of the ODE solving if we use that kind of normalization checks when learning on the dynamic graph. So there is a theoretical gap for the designing of the time interval normalization strategies. So these two limitations are also kind of the open questions in this work. We say the future research directions. And here's the summary. That's what we did in this work. So firstly, we proposed novel spatial temporal biased sampling strategies to extract the patterns from the continuous time dynamic graph. And then we introduced a new perspective, like to encode such patterns and followed by a contrastive learning-based learning objective to do so, to train the entire things in a self-supervised manner without the using of any labeling information. But anyway, we don't have that in many dynamic graph data sets. Okay, so here's some useful references for the readers to take a look after the workshop. And if you have any questions, just feel free to contact me with this email address. And many thanks for attending today's workshop sessions. Thank you so much.
Yeah. Thanks for the great presentation, and thanks everyone for listening. So I would like to thank our speaker again for the nice presentation, and I particularly like the part where in the end you have a slide on limitations, which people sometimes don't do, but I think it's always important to keep in mind. Not every model is going to be perfect, and there's always like new things to work on. Yeah, so I do have some questions, but I will let the audience ask the question first. Does someone else want to go first? You can just unmute yourself. Yes, sir. Okay. I guess I will go first then. So I have a question on in terms of the time complexity. So you mentioned one of the limitation is the time complexity can be quite intense. And recently, there are some work that look at the scalability of temporal graph networks. So what would be in terms of like big O notation, your complexity?
Yes, we have the big O notations in complexity analyzed in the appendix. I haven't put it in the slide, but if you want to see the analyze, you can refer to our appendix. We have a table to analyze the big O time complexity of each of the components, whatever the sampling, working coding, as well as the contrastive learning. We have that on the appendix. So yeah. And one of the things I have to emphasize that as you can see here, if we introduce the spatial biased probabilities into the work sampling, you can see the runtime increased drastically, and it's also positively proportional to the spent temporal neighbors. So this is, I would like to say that this is also one of our research direction in the future, like to overcome this kind of phenomena in this kind of method, because it's not desired. It's not desired because it's computationally heavy, especially for the cases that we need a large span temporal neighbors. There is a huge gap, but how we can get this limitation is going to be a very interesting question in the future. Yeah,
definitely. Yeah, does someone else have other questions as well? Like I do have one or two more, but I think you have a question, Parma.
Yeah, just a very quick question. Apart from the, temporal aspect, does it have also any other like a storage computational intensity? Because I was thinking that maybe storing the history of sampling for each edges, that is something in addition to the other methods. So I wasn't sure that how much additional memory it will cost.
Okay, so the memory cost the memory cost is okay, but the biggest challenge here, and of course, compared with other modules in this method, whatever the working coding and the constructive learning, this part is the most computationally intensive part. That's the increase of the runtime of the entire model. It actually comes from the right line here. That's when we introduce the spatial biased sampling. Why? Because if I use, let me back to this slide, to a little bit to the beginning slide. Here, okay. So when we're using this kind of sampling strategies, for each of the temporal node, I have to calculate the node degree. But how I can do that? I need to explore its temporal neighbors further. For example, given the target is node U, I want to calculate the degree of B. But to calculate the degree of B, I need to know that B have two nodes, A and C. So that means I have to calculate one more times temporal neighborhood searching, that is this notation, to get the degree of B. So this part is very computational intensive. And more or less it's related to the implementations, because I have to say that in the current implementation in our code, the implementation is very naive. I believe this part can have a more sophisticated implementations to reduce the empirical runtimes. Instead of the big O time complexity, but the empirical always is the practical runtimes. Yeah.
Yeah, I see.
That is another note.
And this one, it should have less complexity than the other method, which is like exploration and exploitation, or
yes. Back to it. So you can see if I
Okay, yeah.
introduce the trade-off, the increase is very minor. Yeah. And the temporal bias sampling is very efficient. That's why many existing works are always purely based on this temporal bias sampling. For example, COW. Otherwise, the COW gonna be as expensive as in our method.
But I think at least it should bring more expressivity to the method, because although that is more efficient, but you also consider the spatial relation in addition to the temporal relation.
So sorry, I don't understand the question.
It incurs a lot of temporal complexity, but at the same time, it should also, I think, at least I guess that it will bring more expressivity to the method, because the works are more efficient.
Yes, exactly. So there is for example, here is the way, like how we can I would say elevate these issues here, is we use we treat the memory for the time. So as you mentioned, the memory we used here is not very obviously the space complexity is not very huge here, but the time complexity is high. But how we can do that? We can use as I said, I can use the space to treat for the time. That is one of the most common strategies used in many algorithms. And same here. So that is also a work that we're trying to explore recently, like how we can do that.
Yeah. Thank you very much. It was very interesting.
Sounds good. Another thing that I was thinking is that, so kind of going back to Farmer's point, I think now we are still in like early stage of temporal graph learning, and there's a lot of things that are not clear. Can you hear me?
Which one?
Oh, no. I'm not talking about the presentation. I'm talking about in general. But I think like, yeah, I like your discussion on the like on the time interval encoding. So I think you have a slide on that. And I think it's still not clear what are the best way of doing the time encoding. Like as you mentioned, if you think it's a lot of slides to go through, but if you think there is a way, like how well do you think the model can perform in terms of like particularly predicting exactly when something will happen? So let's say instead of the standard evaluation where you are given the time and you ask the model like U and V or like the edge level task, instead it's the other way around. So you want to know when this is going to happen exactly at some near future, right? So let's say not like too distant, but sometime in the near future. Do you have some ideas on like what might be a good time encoding for that? Or yeah.
Well, so I think this is a feasible way like to do that, but I would say the time encoding the kind of I would, from my point of view, I think this is a very general concept, like how we can incorporate the time information, or the temporal information, into the consideration during the modeling. So whatever the encoding strategies used, I think the key is how you incorporate this information into your model. Will you treat that as a kind of attribute information, or the temporal information is directly reflected in your modeling process? For example, you use the ODE process or the other kind of strategies. So that's my point of view. But of course, as you said, there are of course many other ways to implement the time encoding. It's not rather than simply use the random Fourier transformation here. Yeah.
Yeah, for sure. Yeah, go ahead.
Question.
Yeah, go ahead.
Are we still taking questions? Can I ask maybe one or two?
Yeah, of course.
Yeah. Could you go back to when you were describing discrete versus continuous graphs? Because I was, if you could go just.
Do you remember which slide?
It was very much towards the beginning.
Oh, okay, this one?
Yeah. But
okay.
So here, you basically are timestamping interactions between the nodes. Or are you timestamping when edges appear? Because it's a bit, so I've seen these continuous time dynamic graphs being defined in different ways. And kind of what I'm trying to understand is, do you have the notion of deleting edges, or do you somehow have the edges? For example, is edge between 2 and 5, does it appear at timestamp 6 and at timestamp 8, or is it always there, but there's some interaction? Are you kind of getting what I'm trying to say? It's a bit unclear for me what you actually mean by timestamping the edge like that.
Yeah, I think this is a very good question. Like how, I could interpret your question as how our method can deal with the edge deletion, right?
Yeah, that I'd be interested in that. Yeah, for sure.
Okay. Let me show you the framework. Okay. So how we deal with the edge deletion? For example, at the t=8, at this point of time, I doing the sampling. I go through the historical neighbors, but at the next time, for example, t = maybe 10. For example, we don't have this edge. But at that time, if I want to learn the embedding of node U, I will do the sampling again. But at that point of time, this edge disappeared. So I don't have the chance to sample the node C in that time. So if this edge is deleted in the time, for example, t=9. So do you understand that, like how? So we're doing the sampling at the time we query the embedding. So if at that time we don't have this edge, then we have no chance to sample that sample node. But in the next time, if some edge added into the network, we then have and that if we query the embedding at that time, we didn't have the chance to sample that temporal nodes.
Okay,
So-
can I explain what I understood from what you said, and then you can confirm if it's like that or not? So you're not really formalizing how edges appear or disappear. You're just
Yeah.
formalizing when the nodes interact. Like you're kind of saying, oh yeah, there was like some interaction between C and U at timestamp 3 and timestamp 6, and let's say at timestamp 10, as you said, like you no longer have the edge between C and U, and you no longer have the information that there was interactions at 3 and 6. So there's kind of like a process going in parallel to kind of your process of like modeling this graph, where
Yes,
kind of edges
exactly.
like come in and go, and then you're just modeling the interactions.
Yes, that is. So
Okay.
this approach is different from, if I remember correctly, there is a recent KDD papers that use the methodology like to represent the dynamic network as the dynamic evolving adjacency matrix. So in that case, we have to deal with the edge deletions carefully because we treat them as whatever the sparse or the compact representations as the matrix. So in that case, if we don't have the formally definition of the edge deletion, then it's going to be very tricky. It's like how you can define the evolution of the adjacency matrix. But in our method, we're just doing the in time sampling. So it can naturally deal with the whatever the edge additions or the deletions from the network because we just focus on the dynamic structures at that point of time that we query the embedding. Yeah, as you said.
All right, thank you.
Yeah, are there any other questions? If not, we can wrap up the meeting for today. And yeah, and we'll go back to the 11 a.m. time next week. And yeah, thanks everyone for joining the meeting today, and great to see you all. And yeah, so yeah, see you at next week's reading group.
Thank you very much.
all.
Yeah, and thanks our speaker Ming again for give a great presentation.
Yeah, thank you, Andy.
Thank you.
Thank
and
you.
all to come today. Yeah, thank you.
Thank you.
Okay.
See you
See you.
guys. Bye.
Bye.